Okay, we've been working on two problems. One is your application of the Biot-Savart law. Okay, Biot-Savart law, which is a name I hadn't used, but that's what it is. Okay, so if you want to look it up, you can look up Biot-Savart law. You'll see exactly the same thing I gave you, except that one thing I gave you in class last time was wrong. There's a cross R vector. Cross R should have been a cross R hat, but should be cross R divided by magnitude of R. Okay, vector R divided by R. So you want to do that. Otherwise, you got like a reciprocal R cubed in the thing, which doesn't make any sense at all. I wrote it down carelessly and didn't think it through. My fault. Okay. Now we have the same situation we saw last time, a current in the X direction, let's say, and an arbitrary small increment of that wire that's carrying current. So it's small length increment. We multiply the current by the length increment, and that's the source of our magnetic field. Okay, we're going to let X sub I be the sample point within our delta L interval. And we're going to try to find the field at point XZ. So what I ask everybody to do is make up their own values for I, delta L, XI, and XZ, and find the delta B, the magnetic field due to the current in the delta L increment. Okay? And people making good progress on that, making some mistakes, but we'll work those out so you know how to actually use this law. Okay? And then we're going to develop an integral, but maybe not this time. Okay, because we're having a little trouble with the idea of the dipole field. Okay, so we want to do some calculations to understand dipole field. And of course, that involves using Coulomb's law. And people are having a little trouble using that as far as a vector form. So, it tells me that I've made a good choice for what to do because it's something you really need to know how to do. And it's not difficult. Once you see it, it's the same every other time you see it. Okay, as far as point charges anyway. All right, so I've got a charge Q and a charge negative Q. On the x-axis, at the points A sub 0 and negative A sub 0. And then I've got a series of points labeled around here. Now I've read all the points. I think people have them down, but let's just start by focusing on the point 0A, which is here on the y-axis. So you got charge negative Q, charge positive Q in the point 0A, and we want to find the field at the point 0A. Now, people are thinking about too many things. When I say find the field at the point 0A, people still thinking about these other points. That's natural. You doing it, I would have done it. Okay? Of course, I would have figured it out a lot faster, but you know how it is. So, I would have been a bit distracted and confused, just like most of the rest of us. Okay? You need to learn to focus on one thing at a time, especially when you're dealing with electric fields due to point charges at discrete points. Okay? So, then I said, focus on one of your charges. You pick either one and figure out what the electric field is at the point 0A due to that charge. Okay? So, the natural choice, and what I saw most people choosing, is choosing the positive charge, the charge Q at A0, and then find the field at 0A. So I'm going to isolate that. And I recommend you always have a picture. Yeah, you all should have a picture of this. Okay, I saw lots of calculations without the pictures. Calculations look pretty good. If you don't have the picture, you lose something. Okay? And you failed more relevantly than losing something, you fail to gain something that could be gained by sketching the picture. And I'm failing to write anything because I failed to Keep up with my chalk. Okay, so let's do an enlarged picture here. Here's the point. A0. Here's the point 0A. You have a charge Q at the point A0. Electric field at 0A due to Q is A. Let's write it out. E equals K Q over R squared times the unit vector R divided by its magnitude. And why is that the electric field? Because the electric field is the force per unit charge. When you think of the electric field, you think of a test charge, just whatever charge happens to be there at one time or another, and call that capital Q, say. Okay? So that your Coulomb's law would say that the force between these is K times your charge small q, which is at the point A0, times the charge big Q divided by R squared times the unit vector. That's Coulomb's law. And that would give you the force. If you want the force per unit of test charge, how much force do you get per unit of charge if you put charge at the point 0A? That's the question you're answering with the electric field. You multiply that charge by the electric field and you get the force. Well, that means if you've got the force, which is KQ, little q, big Q over R squared times the unit vector, and divide by the big Q charge, you're left with K little q over R squared times the unit vector. Okay? That's where this comes from. I guess I should probably write that out. Force in a test charge at 0A due to Q is F equals K times Q times big Q, and we'll call the test charge big Q over R squared times R divided by its magnitude unit vector. There's your force. So the electric field is the force per unit of test charge at that point. Force per unit of charge you would put at that point or could put at that point. Whatever charge you put at that point, you multiply by the electric field and you get the force. And that's just K times little q over R squared times your unit vector R divided by its magnitude. Okay? So it all comes down to just what is the R vector? Well, the R vector starts at the location of your charge. It goes and ends at the point at which you're calculating the field. So there's your R vector. What's the R vector? I'm going to say it's negative AI plus AJ. If you want to use a different notation, if you want to use parentheses, you negative AA and you put an arrow over it. Or using bracket notation, which can be a little ambiguous. Officially, you're kind of okay with the pointed braces around negative AA, and I still say put a vector over it to make sure you can spot it. Okay? You can't be too redundant. And I don't think that would cause any confusion. Okay, now I'm going to write AI, negative AI plus AJ. I'm not going to use that pointed brace notation. because I want to be very explicit about separating components. And I think it's more, had the right word, it's more something good if you separate things out. Okay. So there's what you have. Well, now you can do this calculation. You just plug things in. Okay. So E equals 9 times 10 to the ninth Newton meter squared per Coulomb squared. If you ever forget what the units of E are, just think of what are the units of Q and R squared. The units of K have to cancel out the units of Q in the numerator, R squared in the denominator, and give you units of force. Force per unit charge. No, force per unit charge in this case. In any case, you multiply then by, well, I started to put the numbers in with units, but I am not having you do these with units. I was having you do the Biot-Savart law with units, so I forgot where I was. I just neglected that. It's K times Q over R squared. What's R squared? Well, R squared is the magnitude of R. R is the hypotenuse of a triangle with legs A and A. So it's over it's over the square root of 2A squared, but it's R squared is sum of the squares of the hypotenuse of the legs, and you get Q over 2A squared. And then R divided by its magnitude is negative AI plus AJ divided by the square root of 2 times A, and you get KQ over excuse me, 2 times the square root of 2A squared multiplied I'm going to change that in a minute. Okay, this vector over here, I can divide through by A and I just get I plus J, negative I plus J over the square root of 2. And I didn't need the square root of 2 over here. What was I thinking? Okay. So anyhow, you just put the numbers in, expressions in, and you get this. It's in the direction of negative I plus J. And you could even draw it up here. And you could bring the square root of 2 over here with the 2, which I started to do. But I thought it better to leave it over here where it's more obvious. Now, I want you to do the same thing for the charge at negative A, 0. Charge is negative Q do the calculation, finish the picture. Okay, so yeah, I mentioned that there's asymmetry to this thing I'd never really thought about. And it's a little disturbing, but I'll try not to seem too disturbed right now. I'll wait till this afternoon. Okay. Uh, but the one comment, somebody was talking about the square root of 2 in the denominator here, in the 2 here. Why is the 2 here? Why is there a square root of 2 here? Well, there's a 2 here because the magnitude, well, r squared, magnitude of the vector here, is the sum of the squares of the two components. Pythagorean theorem. A squared plus a squared, which is 2a squared. And the square root of 2 here comes because negative ai plus aj is not a unit vector. Your r is not a unit vector. It's got magnitude equal to the square root of 2a. Okay? So if I divide by the square root of 2a, I get a unit vector, and it should be clear to you that negative I plus j over the square root of 2 is a very familiar form of a unit vector. Okay? Now, doing the calculation for negative q, I'm going to call that E2. It's k times negative q over r squared times r divided by r. But what I mean by r, I mean the r vector from here to here. So I'm going to make a little quick change in notation. I'm going to call the vector we used for the field due to the charge q, I'm going to call that r1. And then I'm going to call this r2. Put a tiny 2 on there and say, here's my vector, R2, that I'm using to calculate this. Well, that's going to equal negative k times q over 2a squared, because this vector obviously has the same magnitude as the other, has legs of equal length, but the unit vector is going to be I minus j over the square root of 2. And if you picture it, if you have a positive test charge here, it's going to be experience a force down and to the left to the point negative a, toward the point negative a0. Now, what's going to happen if you add these two vectors? What's the direction of the sum going to be? Okay, a vector pointing up to the left and a vector pointing down to the left. There's a lot of symmetry. Put those vectors head to tail and get the resultant. Do that. Just write that down for me. Just jot down a picture of how you sum these. You can use a parallelogram method or a head to tail method. I wasn't real specific on the picture that I wanted, but I was talking about up and to the left and all that. Now, some people use the R1 and R2 vectors and do a decent representation of that, but we're trying to get the electric field. So we want the E1 and the E2 vectors. So if I draw my E1 and my E2, one at 45 degrees above, one at 45 degrees below the horizontal, equal magnitudes, because you do the calculation, magnitude's going to be negative. There's going to be k times q over 2a squared in both cases. So if I want to add these vectors, I can do it like this. I can do E1 E2, which I came up a little short on because it was kind of in the way here, but here's E total. And it's horizontal. I drew that correctly. And my picture's a little tilted. Okay. Because of the thing I mentioned. If you want to do the parallelogram method, you do this. There's your E total. And if you're not visualizing that when you add two vectors, you're making a big mistake. You're not seeing it, which makes it very, very difficult to develop much intuition about vectors, okay? You might be able to calculate it, but can you see it? I remember when I was a freshman in a good, very, 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 very good, very highly rated school of engineering technology and stuff. They made us sit down and draw pictures of vectors. Well, I'd done enough vectors in high school. They do those pictures in my head backward and forward, and I thought that was Mickey Mouse. I could do all the calculations. I mean, not as far as cross-producting stuff, not really. But as far as just plain old adding vectors and combining them and stuff, it was so obvious to me. But I realized that they had to do that, even at right next to top-rated school of engineering technology, okay? So I keep reminding myself that not everybody sees this as second nature. It needs to be second nature. So you don't keep stumbling over the picture, all right? Now, the calculations, we're looking pretty good. I didn't look at your latest set of calculations, but I assume they looked a lot like this, maybe with a few more details. So that's how we calculate the dipole field at this point. I want you to do it for these other points, particularly the point XY. And the point 0y and the point x0 are also important. And start by drawing the pictures. Like if you use the point 2a, 2a, everybody see that? What's your R vector? Well, it's from one R vectors from the Q vector at A0 to the 2a, 2a point. That vector is going to be I plus 2j. Well, AI plus 2aj, right? Your vector negative Q is going to be longer. Okay? Unlike the case we just saw. So that the attractive force back this way is going to be much less than the repulsive force from Q. Okay? The R vector from negative Q up to 2a, 2a is 3ai plus 2aj. The magnitudes, the two vectors, magnitude of the vector from Q up to here is the square root of 5 times a. Magnitude of the R vector from negative Q up to 2a, 2a is square root of 10a. No, square root of 13a. Okay? So that the attractive, well, the field toward negative Q is going to be a lot less than the field away from Q. And those are the things I want you to see about the dipole field, partly because the dipole field of a magnetic source has a very much analogous shape to the dipole field of electrons. And the dipole field of the magnetic dipole, which really is thought of as being the field due to a current running around a little tiny circle, is a little harder to visualize. Okay? And since we're going to be dealing with magnetic fields in lab, I want you to be able to visualize the field. So I want you to do this much to help yourself prepare to visualize the stuff we're going to do. Incidentally, another thing in the AI description, in mentioning the AI summaries that I've been posting, somehow my SharePoint has changed all my links to files on my computer as opposed to the internet. And I just discovered that. So I've corrected it in a way that I don't think SharePoint can mess up. Okay. There's a little confusion because when I tell it to make the link, I just click on an icon and tell it to make the link. And sometimes it makes a link to the internet. Sometimes it makes a link to the file on my computer. And I thought I knew when it was doing that, when it wasn't. And I swear I fixed it all and it changed it back. But I could be wrong. So if you haven't been seeing those, they're worth looking at. They give you a real quick summary, especially recent ones. They give you a quick summary at the beginning, and they give you a synopsis at the end of things you got to watch for and things you ought to pay attention to. And they're pretty good. Now, sometimes they say things that I don't. I'll usually make a note of it. I'll either say, that's pretty good, or I'll amplify it a little bit because it doesn't say enough. So that my comments are in italics. And that all leads up to the fact that it talked about Faraday's law. Okay. Faraday's law is that thing where the time derivative of the flux is equal to the magnetic field, to the voltage around a loop. Okay, thing I talked about last time. I also said that the one, your multivariable textbook was saying that wrong. Okay. Now I got to thinking about it and I said, I wouldn't have really paid attention. It probably said it right. Because I don't think it was using flux. I think it was taking the derivative of the magnetic field, which is the electric field. Okay. So you still got to watch out for anything I say, for anything AI says, for anything any author says. Okay. And the other thing is, I might have said, I might not. That law is called Faraday's law. Okay. And it used Faraday's law where I hadn't used the terminology. So put a little note in there. Yeah, that's the term. Okay. You've got set 3 down pretty well. Sets 1, 2, and 3. Got all that in your head? Because you're going to need it. Okay. It's going to help you visualize what's going on and all the stuff we're going to see in lab. Okay. Gotta stop that.